Now that you've got your Newton's second law for rotation, it's time to do a little bit of problem solving. This is our equivalent of what we did for Chapter 2 and forces. Before I even get into the step-by-step process or give you examples of how you're going to approach this, there's something really important that you need to know. And just like kinematics, it's about the units. All right, make sure that when you're plugging in values, that you're plugging in values with the correct units. Radial acceleration is radians per second squared. Torque is meters times newtons. Moment of inertia is kilogram times meters squared. If you don't plug in with consistent units, your answers are going to be so far off it's going to hurt. If you don't write down your units when you problem solve, you're not going to notice it. I don't like calling problem-solving strategies the rules, which is why I put them in quotes, but it just gives you a general step-by-step of how you're going to approach it. And it should look identical to how you problem solve every single time you try and problem solve. You're going to draw and label a diagram. That's the first step every time, no matter what type of physics you're doing. Now that our systems have gotten more complex, you're going to have to decide what your system is and what objects are part of that system. Because, just like we did for work and energy, you're going to have systems that involve more than one item. So, for each of the items or objects that you need, you're going to be drawing a free body diagram. And this is important, and it's not only important for problem solving, but it's also important for points on an AP exam. You only want to show on an object the forces that are acting on that object, not the forces that are being caused by that object. Make sure that you show the forces that act on exactly. The position matters, exactly where they're acting. This is important so that you can find torque. All right, that means that if you've got an object and it's experiencing torque at that position, then you want to draw that force right where it's happening, not toward the center. We're no longer treating these things like spherical cows, except when we're talking about gravity. Gravity still always acts on the center of gravity of an object. So you can always still draw your gravitational force right at the center. Friction. Where does friction act? Oh, friction acts exactly at a contact force position. Normal force. Normal force acts from the table surface. So make sure that you're being that specific. Once you've done your free body diagrams, you're going to, for a rotational motion problem, figure out the axis of rotation so that you can calculate your torques. The axis of rotation is the point at which the rotation is originating from. On a door, it would be at the hinge, and on a disc, it would be spinning from the center. If you're picking up a barbell, it would be the position from the ground that it's braced. And then when you're calculating your torques, make sure that you set a positive and negative. Conventionally, positive is counterclockwise, and negative is clockwise. Then you're going to apply Newton's second law for rotational objects, which is the net torque is equal to the moment of inertia times the rotational acceleration or the radial acceleration. If your moment of inertia isn't the unknown, so if you're not using that equation to solve for your moment of inertia, then you're going to have to use the handy chart to find and calculate the moment of inertia. And make sure that when you do, you're consistent with units. Don't forget to change your centimeters to meters. Don't forget to change grams to kilograms. It's going to screw up everything if you do that. You're going to apply Newton's second law for translational motion also, because some problems will have both rotational and translational motion in them. In fact, the lab that's coming up for you guys is going to be exactly like that. And we're going to take a look at some example problems where that occurs. You're going to apply, you're going to make sure that for any equation that you have, even if you have to use substitution, you're going to solve for all of your unknowns. And once you have your values and you have your units for your values, take a look at them and decide if they're reasonable. So as promised, let's go ahead and let's take a look at an example of doing exactly that step-by-step procedure. Here we've got a heavy pulley. All right. The force getting acted on the heavy pulley is a force of tension, and that force of tension is acting right at the radius r, and that radius r is 33 centimeters. And that force of tension is a constant 15 newtons. The pulley itself has a mass of 4 kilograms. It is a heavy pulley. It's like heavier than your cat. If the pulley accelerates uniformly from rest, well, then that means that initially it wasn't rotating. So its initial rotational velocity was 0 radians per second. And then once it was done accelerating from rest, it was experiencing 30 radians per second. Now I check my units. Radians per second are the correct units for rotational velocity, so I'm going to leave them as is. And that acceleration occurred over the course of 3 seconds. But it didn't occur exclusively from this force of tension. There was a resistive force from friction that occurred at its point, and that force of friction at the radius that it acted gave you a torque of 1.10 meters times newtons. So we want to know, given all of this information, can we find the moment of inertia of this heavy pulley? And the first thing that I want to look at is if this is where the force of tension is acting, this is the force of friction acting given, and it gives us this torque value. This is the radius of the circle of the cylinder, and it has mass m. And I know that the relationship between torque is that the net torque is given by the moment of inertia times the angular acceleration. So I'm going to need to find the net torque. And the net torque in this situation is given by this force down here is going to cause a counterclockwise rotation. So that's going to be a positive torque from the tension. And the friction is a resistive force. The friction is resisting in the clockwise direction, so that's going to be a negative torque from friction. And I also am going to need to figure out the angular acceleration. Angular acceleration could be given from translational values, but I wasn't given any translational motion values. I was only given initial and final angular velocity and time, so I'm actually going to be using those, W minus W naught, or omega minus omega naught divided by the change in time, and that's going to be equal to 30 radians per second minus 0 divided by 3.0 seconds. 30 divided by 3 is 10 radians per second squared. So that was a pretty straightforward calculation. Let's go ahead and let's do our net torque. Alright, this torque of tension is given as the force of tension times the moment arm. And lucky us, we're not going to have to find any angles because that is a perpendicular relationship right there. So it's just going to be that force times the radius of the instrument. And the torque of friction is already given. So it's going to be torque of friction going to be 1.10 meters times newtons. So I can plug that in and I get 15.0 newtons times 0.33 meters minus 1.10 meter newtons, and that will give us our net torque. And if we calculate that out, it's going to be 3.85 meters times newtons. So that's my net torque, that's my acceleration. I can actually solve really easily now for my moment of inertia, because if I rearrange this equation here, then I get the moment of inertia is going to be equal to the net torque divided by the radial acceleration. Net torque is 3.85 meters times newtons. Radial acceleration is 10 radians per second squared. So I actually get that my moment of inertia here in this situation is 0.385 kilogram meters squared. And that's an experimentally determined moment of inertia. That's not too bad. If you did a rough estimate, you'd say that this object is pretty darn close to a uniform cylinder. And from our handy-dandy chart, we know that the moment of inertia for a uniform cylinder would be 1/2 mr squared. So that'd be 1/2 times a mass of 4 kilograms times a radius of 0.33 meters squared, and that would give us 0.218 kilograms meters squared. And we see that these values, they're not exact, and you're almost never going to find a situation experimentally where it's exact, because there's grooves and divots and this isn't a perfect cylinder. But they're of the same order of magnitude, right? They're both 1/10, so that you can feel pretty confident in your value. So we're going to keep this value in mind for our next problem. Once you've determined experimentally what a moment of inertia is, you could use it to solve for a more complex problem. And that's exactly what this next problem is. It's a more complex problem. And this is a pulley and a bucket. And in this situation, you've got the same pulley. It's the exact same setup. So that means that the moment of inertia for this pulley right here is going to be the exact same moment of inertia that we just calculated. But this time, instead of a constant 15 Newton pull, what you're experiencing is the bucket itself has a weight force of 15 newtons, which means the mass of the bucket is 1.53 kilograms. And that force is causing the pulley to accelerate. So what we're going to do is we're going to assume that the cord has negligible mass so that we don't have to do any calculations there. We're going to assume that the cord is rolling down without slipping or stretching, and we're going to assume that the force of tension is caused consistently, it's not stretching. And we're going to calculate the angular acceleration of the pulley with this particular situation. And we're also going to calculate the acceleration of the bucket, because if the pulley has a rotational acceleration, then that means that the bucket is going to have a translational acceleration. So we're looking at a situation that's very, very similar to our original situation. We've got two objects, so we want to make sure that we've got all of our values. Here we've got the frictional torque. Here we've got the force of tension down, and that's going to cause some sort of angular acceleration of the bucket, the two torques here. The bucket itself has two forces on it, the force of its weight and the force of tension, and we know that that bucket is experiencing a net force because it's accelerating. It has a tangential acceleration downward. It started from rest and is sped up. So we're going to need the net force of the bucket, which is if it's accelerating downward, and we'll set downward to be our positive direction. Counterclockwise is our positive direction for the rotational motion. That's going to be given by mg minus the force of tension, and that will equal the mass of the bucket times the acceleration of the bucket. So that's one calculation that we have to our benefit. We also know that up here, the net torque is given by the torque from tension minus the torque from friction, and that is going to be given by alpha, a moment of inertia times rotational acceleration. So we don't know what the tension is, but what we do know is we do know that there is a relationship between these two free body diagrams, and that relationship is the force of tension, right? Because this is the force of tension times the radius that tension occurred at, which we know from our previous problem is the force of tension times the radius of the instrument, minus the torque from friction will equal the moment of inertia times the radial acceleration. So I can solve this value down here for the force of tension. The force of tension is going to be mg minus ma. Okay, well, let's go ahead and let's plug that in there, and I get mg minus ma times the radius of that pulley minus the torque of friction, will equal the moment of inertia times the radial acceleration. Now, before you get too worried about the fact that you've got the mass of the bucket here and you've got the acceleration of the bucket and you've got a radius, there's a lot that we do know here, and one of the things that we know is the relationship between the tangential and the radial acceleration. This is rolling without slipping, so I know that A equals R alpha, so I'm going to go ahead and I'm going to plug that in, and here our radius is the radius of the pulley, so it's going to be mg minus m r alpha times the radius minus torque of friction equals moment of inertia times alpha. Now, mg is 15 newtons times the radius of the bucket minus m/r squared alpha minus the torque due to friction equals moment of inertia times alpha. I've got two terms here that have my rotational acceleration, so I'm going to rearrange the equation for that rotational acceleration, and I get moment of inertia times radial acceleration plus mr squared alpha equals 15 newtons times the radius minus the torque of friction, which I'm going to plug in as 1.10 meter newtons. And if I factor out my radial acceleration, then I get that my radial acceleration is going to be given by 15 newtons times the radius, which is 0.330 meters minus 1.10 meter newtons divided by the moment of inertia minus m/r squared. I have a value here. It's the moment of inertia that I calculated previously. So it's 0.385 kilogram meters squared. And then I have this mass right here is 1.53 kilograms. And this is 0.330 meters squared. And that means it's going to be squared. So plugging in and solving, I get that my radial acceleration is 6.98 radians per second squared. And that's the angular acceleration. It's actually less than we had before when it was a constant 15 Newton force. And that's because the force of tension is actually going to be less than 15 newtons, since it's the net force of the tension and the weight of the bucket. So the acceleration of the bucket is less, the acceleration of the pulley is less. And now, tangential acceleration is going to be given by our relationship for rolling without slipping, R alpha. So we're just going to take that 6.98 radians per second squared. We're going to multiply it by 0.330 meters, and we get an acceleration of 2.30 meters per second squared, and that is the acceleration of the bucket. So you can see that having two systems where you have a concise set of units for substitution is going to give you a whole new realm of problem solving.